Okay, so now let's talk about how we could attain a little bit of rigor for what we are doing. So I don't want to go through the Newton's algorithm and introduce the errors rigorously. Instead, what I want to do is to talk about how we can check for equality when we have approximate numbers. But the problem with approximations is that you shouldn't be able to decide equalities. For example, if alpha and beta were equal and you were just approximating alpha and beta, then you would just see that both your approximations agree more and more, but typically you cannot decide on equality. This argument would be true if alpha and beta were arbitrary numbers, then there really is no standard way to do this. But when alpha and beta are the roots of polynomials with integer coefficients, so they're algebraic numbers, then in fact approximations will be sufficient. So first of all, since both alpha and beta are algebraic numbers, they annihilate polynomials with, say, integer coefficients or rational coefficients, so I'm choosing alpha to be a root of p and q to be beta to be a root of q. So the minimum polynomial, if it's monic, for example, let's say monic is usually built into the definition of a minimal polynomial, then if p is not the same as q, then already alpha is not the same as beta. So when we are dealing with algebraic numbers, if we are keeping track of their minimal polynomial, then already we have to decide an inequality between just integers essentially. I just have to compare the coefficients of p and q. But once p and q are the same, then we're in the domain of having to approximate the roots. Now, when the minimal polynomials are the same, and I have an approximate representation of alpha and beta, so what am I supposed to do? Can I decide equality? Or could the roots be arbitrarily close somehow? Of course, this is not much of a problem if you don't set it up correctly. So I'm saying someone has given me approximations of possibly two different numbers, alpha and beta, and they're telling me that their approximations are within the convergence basin for Newton's approximation method, and my job is to decide whether or not the two approximations are supposed to represent the same number. So let's be precise. Okay, so someone has given us approximations of the roots. We want to use these approximations and the polynomial p to decide if this alpha tilde and beta tilde are in the same convergence basin. So that would mean that they're approximations of the same root. So if alpha and beta were not the same, then it would make sense to do the following. Of course, we wouldn't know this, but it would make sense to just sharpen our approximations by doing Newton iteration. Eventually what happens is that successive approximations will be moving further away from each other. So what we can say is that our successive approximations will lie in some ball B for alpha, and the approximations for beta will lie in a disjoint ball. So eventually we will be able to catch up onto this fact. Once we realize that they're converging to different numbers, we will be able to choose these disjoint balls, and this will tell us that alpha and beta are disjoint. So one strategy would have been just to sharpen our approximations. But the problem is, we don't know a priori if alpha and beta are different or not, and we tried this maybe 1,000 times, and they still look to be the same, so we cannot find these disjoint balls. When do we stop, right? So we need a point to stop and say, well, at this point, alpha and beta must be equal if we couldn't find this disjoint balls. So to address this problem, let's make the following definition. Given alpha, so root of its minimal polynomial with integer coefficients, we define h of alpha to be the following. It will be the maximum of the absolute value of the coefficients of p. So let's write it as like so, where p is written like this. Remember, I have integer coefficients, so I did not ask for it to be monic, but I would like the GCD of these numbers to be 1. Okay, so this is called the naive height. And here's a very interesting, very simple, but very quite powerful result is the following, that with alpha and p as above, if alpha is non-zero, so p is non-zero, then the norm of alpha is greater than 1 over 1 plus h of alpha, and that's also bounded from above by 1 plus h of alpha. So before we prove this, let's talk about how we are going to use it. So if we say gamma is alpha minus beta, so remember we had two algebraic numbers, alpha and beta, then we can say there is this minimal polynomial, maybe r of x of gamma. Now if gamma is non-zero, then the absolute value of gamma will be greater than 1 over 1 plus h of gamma. Yeah, so the only thing we'd have to do is to approximate alpha minus beta, and we have sharper and sharper approximations of alpha and beta, so we can approximate this difference via our approximations. If our approximation has norm less than 1 over 1 plus h gamma, then in fact this condition is violated, which means gamma has to be 0. So we are able to check absolute equality by approximations. Further remarks to use this lemma properly. So first of all, I did not mention this point, but because we were sloppy in constructing Newton's algorithm, but it's not so hard to say that once you're in a convergence basin, you can bound the distance of your successive approximations to the root. So once some upper bound here. So and here I mean perhaps you want to apply the Newton algorithm a few more times here, but then eventually you'll be able to bound the difference by some explicit number. So that will come in handy here. To bound alpha minus beta, you would instead bound alpha tilde and beta tilde. And the second point, which is a little bit more delicate, is that when you know bounds on h alpha and h beta, then you can find bounds on h gamma. So there's an explicit formula that bounds h gamma both from below and from above using h alpha and h beta. You also need to use the degrees of the minimal polynomials of alpha and beta. So here gamma was the difference or the sum, it doesn't matter. So p and q can be different in fact. So there's an explicit closed formulas, right? So they're slightly more involved to derive, so I will not do this today. But it will not be a problem. So we will see another method of computing gamma later on. So anyway, so equipped with these facts, I'm able to use this lemma as indicated in this red command. Okay, let's prove this lemma. So this is super easy and quite powerful. So I'm going to prove something slightly more strong. So I'm going to just take any polynomial that annihilates alpha. The difference here is that I'm not assuming that p is the minimal polynomial of alpha. So p of x is once again going to be just a0 xn, a1 xn minus 1 up to a0, and then let h be some number that bounds to the maximum of these numbers. Okay, so now I'm going to prove the lemma. What you have to use is that alpha is of course less than or equal to a0 times alpha, its norm, because a0 is in an integer, so at worst I made this thing larger. And now, since p of alpha was 0, I'm going to substitute something else here. I'm using that p of alpha is 0, so that a0 alpha n plus blah 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 plus a0, oops, this is a n equals 0, this is n. And now I can attain a0 times alpha if I multiply this expression by alpha to the minus n plus 1. And then collecting terms on the right, I get... Well, okay, so I kill this minus sign. I'm going to collect all the AIs by substituting this h. So let's do this in 2 steps. Using triangle inequality, this is a1 plus a2 alpha plus this is minus 1, this is minus 1, an. Yeah, so now I substitute h here. And this is a geometric series, a part of a geometric series. So here maybe I could have had equality, that's fine. So here I'm going to have an inequality. I'm just going to sum up to infinity. So I'm assuming alpha was non-zero. So that was one of the hypotheses in the lemma. So I say this is h. So this is up to infinity now, and this is just h divided by 1 minus alpha minus 1. Well, okay, so I just multiply the left-hand side by 1 minus alpha inverse to find the following equality. So we get this, which of course implies... So this gives us one of the simpler inequalities, that the norm of alpha is bounded by h plus 1. But we can do a little bit better. So if we let q of x to be... So what do we want now? a0 plus a1x plus blah 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 up to anxn. So I've taken p, but I've changed the monomials. And of course, q of alpha inverse is going to be 0. Yeah, so this is how I've engineered q. On the other hand, the height of q, so the maximums, is again bounded by h. I mean, I'm just going to use this inequality that we've already derived. I can get alpha inverse, so the norm of this root, is bounded by h plus 1 again. So because h bounded these coefficients. But now this implies 1 over h plus 1 bounds the norm of alpha. And this concludes the proof. Okay, yeah, so this was what we wanted. I've proved something slightly stronger, but it was evident, so I could substitute not only a bound of h of alpha, so something greater than h of alpha here, that's clear. I could have used any polynomial, not just the minimal polynomial, to derive such a bound. So this can be more efficient so if you don't want to compute the minimal polynomial of alpha. Now, if you're interested in this kind of bounding of numbers, their distances, to bound maybe the naive heights of sums of algebraic numbers of their product, or even far more general, what you can do is take any polynomial expression, multivariate polynomial expression, substitute algebraic numbers such as alphas, betas, whatever. You can bound the norm of this substitution explicitly using heights. So you can do more, let me say. So if you take a bunch of algebraic numbers, you take a multivariate polynomial with integer coefficients, you can bound. So you can bound this expression explicitly from above and from below. So let's say if it's non-zero, you just need to use the heights of alphas and of course their degrees and the height of f. So heights and degrees of alpha i's, and of course the height and so the size of the coefficients of f and its degree will also factor in. But there's a clean formula. So if you're interested in these kind of results, a very good reference is the book of Waldschmidt. The book was called Diophantine Approximations on Linear Groups, whatever. So this is enough information to find the book. And what I described upstairs is taken from its chapter 3. So he's interested actually on attacking transcendental numbers. So of course this situation with algebraic numbers is its foundation. So you can go quite far with this kind of construction. All right, so that was a hint about how you can attain rigor even when you're dealing with approximations, which is the reason why you should not treat these numbers as approximations once you know you are in the convergence basin of the Newton iteration. So basically, in other words, a root together with the knowledge that it lies in a convergence basin is good enough to do rigorous arithmetic, which means we should treat it as a root. I mean, it's as good as an exact root. It's almost harder to do arithmetic with radicals, right? So far, we've been discussing a very simple version of Newton's iteration, but in fact, it can be generalized. So I thought I should at least tell you that it can be generalized and how it works. So we would like to generalize it from univariate to multivariate. So suppose we are given a polynomial map from Cn to Cn. Right, so this is each entry is a polynomial. So then we can use Newton's method to find roots of this polynomial system. So that means points in Cn such that each of the polynomials vanishes. We're going to approach this problem later on from using Röbner bases, but just I would like to briefly mention that Newton's method works here too. Of course, there are all sorts of hypotheses, like the roots should be somehow isolated or the derivative of f vanishes. So there are some conditions for Newton's method to work, and then making this rigorous, so to understand when you are in a convergence basin, that kind of thing actually takes some work. But let's just get the simple idea. Again, I take beta from Cn, so now this is a tuple of numbers. And suppose I'm close to some root of this polynomial system. And further, I'm going to assume that the derivative of this polynomial system is invertible. So this previously, the derivative was a 1 by 1 matrix, and therefore it was a number, and invertibility was it just being non-zero. But right now, this is going to be an n by n matrix, so I'm talking about its derivative being non-zero, so this is df evaluated at alpha. Then there's something, a higher dimensional analog of Taylor's expansions. So this Taylor series says that, first of all, f of alpha, which by definition is a root, so this is identically 0. This I'm going to approximate at beta, so I write f of beta plus, and here's the thing, you say this is going to be d of, so this is going to be the linear map df evaluated at beta applied to the vector alpha minus beta, and so on. And so this is just well, actually the so on part becomes more interesting because the higher derivatives are somewhat more interesting. But nevertheless, the higher dimensional version of Taylor series exactly looks like this, so it mimics the one variable case. And now we change equality to approximately equal, as we did before. So we say 0 is approximately f of beta plus d of f beta times alpha minus beta. And then here I'm removing the remaining terms. And that's why I assumed that beta was close to alpha, so that means these remaining terms, these should be small. And hence the approximation here. Well, now I can solve for alpha because df of beta should also be invertible if df of alpha is invertible. Since these are continuous expressions, if this has non-zero determinant, this should have non-zero determinant provided beta is sufficiently close to alpha. Again, I solve that alpha should be approximately. And so this is the formula that mimics our previous case. So I take beta, so I inverted this thing by applying this map to the left. I get 0, df inverse beta here. This is killed, I get alpha minus beta here, and then I collect terms. So alpha equals beta minus df beta inverted applied to f beta. Right, so this is a vector of size n, this is an n by n matrix, this is a vector of n. Right, so this is approximately alpha. And then the method, so Newton's method, is to simply take this to be a better approximation to alpha than beta, and then repeat by substituting this better approximation in terms of beta here. And it turns out that there is again something called convergence basin where you approximate alpha beta better and better. Again, the error decreases quadratically. Alright, so this is also an extremely useful tool, and this idea was made practical and rigorous in Smail's paper. So this Smail's paper, what it's trying to do is that it wants to be able to decide whether or not beta is in a convergence basin of some root based purely on information at beta. Since you don't know where alpha is, you don't know even if you're close to a root, the only thing that's available to you is your starting point. So you should be able to decide just based on this point whether or not you're in a convergence basin of a root. And he was able to describe how to do this, and then the subject took off. So it's very nice. Okay, so what we have done so far is that we've seen that Newton's method typically works, but there are all these problems, and it works extremely well only if you're already close to a root. So then maybe we should find some other method to get close to roots and then apply Newton's method. And so this is what people typically do. And then the question is, how do you get close to all the roots? And I will only sketch the idea. So first, let me give you the keyword. The keyword is homotopy continuation. So it's all the rage these days. It's very successful in solving even huge polynomial systems. And the point is that you start by solving a different polynomial system. And this, by the way, could work also with a single polynomial. We can talk about polynomial systems, but maybe for simplicity, let's talk about a single polynomial with a single variable. For example, we could take something like x to the n minus 1. So x to the n minus 1 is very good because we know all of its roots anyway. And I start by quote-unquote solving this polynomial. So I just give a good representation of its roots. Then you deform, so maybe let's call this thing q of x, to the given polynomial p of x, r. So this was our polynomial that we wanted to solve. So you can deform it by something like, so I can define this polynomial rt of x. So that's going to be t times q of x plus 1 minus t p of x. This is not what you should do, but this is one simple thing you could do. So you just take a linear combination of these polynomials. Ideally, you should actually take slightly more chaotic coefficients here, because whenever you do something simple in this subject, so when you do numerical approximations, whenever you do the obvious geometric nice thing, it will break your algorithms. So you should actually take an sort of an arc maybe inside of this plane perhaps. So, and the point is to follow the roots here. Sorry, this should have been x of d, not, so x of d, where d is the degree of, the reason I want d roots here is because p of x has d roots, and this polynomial system should have almost always, for almost all values of t, should have exactly d roots. And what we want to do is to start with the roots here and follow the roots as t varies from 1 to 0. Okay, so t here is a complex variable. It's important that it's complex because there will be some values of t where this thing will break. So you want to move around these bad values of t, but you can. So this complex plane will not be disconnected if you insist on having, let's say, d disjoint roots. And here the heavy work is done by this word. How do we follow the roots? If you want to learn rigorously how this following construction works, you should just Google homotopy continuation. But we can give a good idea already here. The point is that you have this t-plane, complex t-plane, and so above some value t0, I have, let's say, a line, so another complex plane, and I have the roots of rt0 here. So these are the roots of rt0, and as t0 moves, these roots move as well. So these would be the roots of rt1. And here's where it looks like I'm cheating. I do not want these sheets to come together. I do not want double roots. That's where I've used that t is a complex, t lives in the complex plane. Inside of this complex plane, I just need to find a real path between 0 and 1 such that this picture would work. So that this should replace my real path. And what you need to do is at each point, you compute just a tangent vector as to how the roots move. And then you take a very small step in this linear direction. So you maybe go here and you pretend this is your new root. Of course, you've accumulated error here, and you do exactly the same thing. So you don't have to be at a root to compute the vector field here. So you redo your linear approximation of how the roots should move. And if you do this again and again, what happens is that you slightly move away from this path. But if you're taking sufficiently small steps, then it turns out that even when you do this and you sort of moved away a little bit, your error typically can be under control. I mean, it's hard to do this rigorously, and it's a lot of work to do this properly, but it just is true that you can do it. And in the end, so with a small error here, you found your roots. But then remember, we don't need to be super precise, because after this step, we can apply Newton's method. Okay, so this is how you can get close to the roots before you know where they are, so that you can apply Newton's approximation. And also what I've just done here can also be done with polynomial systems. So you just first solve a very simple system, very much like this one. So maybe where every variable is just to some power -1. So every variable is just the root of unity. But it becomes an engineering problem to do this properly. So there are many difficulties when you increase the dimension. You don't, maybe it's an art to choose a good starting system. So okay, it becomes a huge research subject. But the idea, I think it's very clean, that it's something that everyone could understand basically. Okay, we will now end the numerical discussion of how to solve polynomials and this very small discussion of how we could have used Newton's method and homotopy continuation for polynomial systems. We will approach this subject of solving polynomial systems using Gröbner basis at some later date. And next up, we also want to do a more arithmetic approach to polynomial solving. All right, this is where we will end today. See you at the next lecture.